Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should truly expand your mind, gently pushing the boundaries of what you think is possible in our universe. Right now, as you settle in, you're on a planet orbiting a star that is just one of an estimated 100 billion to 400 billion stars in our own Milky Way galaxy. And that's just our galaxy. The observable universe, the part we can actually see, contains at least 2 trillion galaxies, each teeming with billions of stars. If we take a conservative estimate of just one planet per star, though we know now that planets are far more common, often several per star, that's potentially 200 sextillion planets out there. That's a 2 followed by 23 200,000 million planets. Think about that number for a moment. It's a scale that utterly breaks our intuition. When you have numbers that vast, the improbable doesn't just become possible, it becomes inevitable. What seems like a 1 in a trillion chance on Earth becomes a near certainty somewhere in the cosmic ocean. And it means that the most outlandish, mind-bending and truly unusual planetary environments aren't just theoretical constructs of science fiction. They are real, physical places sculpted by the relentless creative forces of astrophysics and chemistry. We are not just looking for Earth-like worlds, we are discovering worlds where the very definition of a planet is stretched to its absolute limit, where the most common elements behave in ways we can barely imagine, and where conditions exist that would shatter our understanding of geology, meteorology, and even time itself. This vast cosmic census ensures that for every familiar rocky world like ours, there are countless others that defy expectation, embodying a strangeness that is both profoundly beautiful and deeply humbling. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious, drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing. This exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with a concept that sounds like pure fantasy, yet is grounded in solid astronomical observation and planetary science. A planet where a significant portion of its entire mass, not just a thin crust, is composed of diamond. Not merely a few scattered gems, but entire mountains, vast plains, and even the planet's mantle all crystallize carbon. Imagine standing on a world where the very ground beneath your feet is the most precious material known to humanity, forged by cosmic pressures and temperatures far beyond anything we experience on Earth. This isn't just a what-if scenario, it's a very real possibility for exoplanets like 55 Cancri E, a world so extreme it challenges our fundamental understanding of what a planet can be. To truly grasp the reality of a diamond planet, we first need to understand what diamond actually is, and how it forms here on our relatively mundane Earth. Diamond, chemically speaking, is simply carbon, the same element that makes up the graphite in your pencil, the charcoal in your grill, and the vast majority of all organic life. The profound difference between these humble forms of carbon and a brilliant diamond lies entirely in the arrangement of their atoms. In graphite, carbon atoms are arranged in flat, slippery sheets. But in diamond, those same carbon atoms are locked into an incredibly strong, rigid, three-dimensional lattice structure. This specific atomic arrangement is what gives diamond its extraordinary hardness, its unparalleled thermal conductivity, and its breathtaking optical properties. On Earth, diamonds form deep within the Earth's mantle, roughly 50 to 200 kilometers below the surface, where temperatures reach over 1,000 degrees Celsius, and pressures are an astonishing 50,000 times greater than atmospheric pressure. These are the conditions required to squeeze and bake graphite into its crystalline diamond form. Now extend that concept to a planetary scale, but with a fundamental shift in initial composition. Earth is what we call a silicate planet, meaning its bulk composition is dominated by silicon and oxygen, forming minerals like feldspar and quartz. Our planet formed from a protoplanetary disk that had a specific ratio of elements, with oxygen being significantly more abundant than carbon. But not all stars, and therefore not all protoplanetary disks, are created equal. Some stars, those with a higher metallicity, a term astronomers use for anything heavier than hydrogen and helium, and, crucially, a higher carbon-to-oxygen ratio in their stellar atmospheres, can give birth to planets with a very different chemical makeup. In such a carbon-rich protoplanetary disk, as the early planet begins to accrete material, the primary building blocks aren't primarily silicates. Instead, carbon-rich compounds like carbies, carbon bonded with metals, graphite, and even pure carbon begin to condense and clump together. Imagine vast quantities of these carbonaceous materials forming the very core and mantle of a nascent world. As this planet grows, its own immense gravity begins to exert incredible pressure on its interior. For a super-Earth like 55 Cancri E, which is about 8 times the mass of Earth and twice its radius, those internal pressures would be many, many times greater than what we find in Earth's mantle. Potentially hundreds of gigapascals or millions of times atmospheric pressure. Combine this immense pressure with extreme temperatures. 55 Cancri E orbits its star incredibly closely, completing a full year in just 18 hours. This proximity means its surface temperatures soar to thousands of degrees Celsius, hot enough to melt rock and, critically, hot enough to melt carbon. So what you might have is a world with a core of metallic iron surrounded by a vast, deep ocean of molten, superheated carbon. As this molten carbon is subjected to the crushing internal pressure, the same phase transition that creates diamonds in Earth's mantle would occur on a truly planetary scale. The liquid carbon would solidify not into graphite but into diamond. This wouldn't be a thin crust, it would be a vast, deep mantle of diamond, potentially kilometers thick, encompassing a significant fraction of the planet's entire volume. The implications of such a world are profound. A diamond planet would be incredibly dense, far denser than Earth, a characteristic that astronomers can actually infer from combining transit observations, measuring the planet's size as it passes in front of its star, with radial velocity measurements, detecting the star's wobble caused by the planet's gravitational pull. Its geology would be unlike anything we know. Diamond tectonics. Volcanoes erupting superheated liquid carbon solidifying into crystal on the surface. Its atmosphere, if it retained one in such extreme heat, might be composed of exotic carbon compounds like carbon monoxide or even diamond vapor. The sheer scale of such a treasure is staggering, yet it highlights the universe's capacity for creating wonders that are both unimaginably rich and utterly inaccessible. We've now glimpsed a world forged from the very essence of carbon, transformed under cosmic pressure into a crystalline giant. But what about planets where the forces at play aren't just about chemistry and pressure, but about the very fabric of space-time itself? How do worlds exist where the line between solid ground and gaseous atmosphere blurs, or where the relentless pull of a nearby star stretches a planet into an egg-like shape, creating internal friction so intense that the entire world glows with heat? That brings us to the fascinating realm of tidal forces and extreme gravitational interactions, which we'll delve into next. Welcome back to Dreamy Science, where we dive headfirst into the universe's most extraordinary corners, challenging everything you thought you knew about planets. Last time we marvelled at worlds forged from diamond under unimaginable pressure. But what happens when the very fabric of space-time, warped by immense masses, begins to pull and stretch planets with an invisible, relentless grip? Today we're embarking on a journey to worlds where gravity isn't just a force holding things together, but a sculptor, a destroyer, and an architect of the truly bizarre. We're talking about planets shaped by extreme tidal forces and gravitational interactions. You know, gravity. It's the force that keeps your feet on the ground, the moon in orbit around Earth, and Earth orbiting the sun. It feels so fundamental, so constant. But gravity isn't a uniform blanket, it's a gradient. The closer you are to a massive object, the stronger its pull. And this difference in gravitational pull across an extended body, that's what we call a tidal force. It's the universe's subtle, yet incredibly potent, sculptor. Think about our own Earth, a planet we consider relatively stable. Even here, you experience tidal forces every single day. The moon's gravity pulls more strongly on the side of Earth facing it, and less strongly on the far side. This differential pull stretches our planet ever so slightly, creating bulges of water that we observe as ocean tides. Twice a day, the oceans rise and fall, a rhythmic testament to the moon's distant, gentle tug. Now imagine amplifying that tug by orders of magnitude. Imagine a planet orbiting so close to its star that the gravitational difference between its near side and far side isn't just a gentle stretch, but a profound planet-altering deformation. This is the reality for many exoplanets, especially those we call hot Jupiters or super-Earths that hug their parent stars in dizzyingly tight orbits. For these worlds, the tidal forces are so immense that they become tidally locked. Just as our moon always shows us the same face, a tidally locked planet presents one hemisphere perpetually bathed in the searing light of its star, while the other remains in eternal frozen darkness. Can you picture it? A world split in two, one side a blazing inferno, perhaps with oceans boiling away into superheated steam, the other a frigid wasteland where any atmosphere might freeze solid and fall as snow. The Terminator line, the perpetual twilight zone between these extremes, would be a place of unimaginable winds, born from the colossal temperature differences trying to equalize across the planet. We're talking hurricane-force gusts that would make Earth's most violent storms feel like a gentle breeze, potentially ripping across the surface at supersonic speeds. But tidal forces don't just lock a planet's rotation, they can also knead its interior like cosmic dough. When a planet's orbit isn't perfectly circular, which is often the case, especially in young systems or those with multiple massive bodies, the distance to its star constantly changes. As it swings closer, the tidal forces intensify, stretching the planet more. As it moves further away, the forces relax and the planet rebounds. This continuous stretching and squeezing, this relentless cosmic massage, generates immense friction deep within the planet's core and mantle. It's called tidal heating, and it can turn a seemingly inert world into a volcanic powerhouse. Look no further than Jupiter's moon Io in our own solar system. Io is roughly the size of our moon, but it's the most volcanically active body in the solar system. Why? Because Jupiter's colossal gravity, combined with the gravitational nudges from Europa and Ganymede, constantly distorts Io's orbit. This means Io is perpetually flexing and relaxing, generating so much internal heat that its surface is a hellscape of hundreds of active volcanoes spewing sulphurous plumes hundreds of miles high. Now extrapolate that to a planet many times Io's size, orbiting a star far more massive than Jupiter in an orbit far tighter than Io's. You'd have a world where the surface is a constant churning sea of molten rock, where continents might be mere temporary features constantly being recycled by cataclysmic eruptions. Imagine the skies perpetually choked with ash and glowing red from the lava rivers below. It's a vision of planetary purgatory sculpted entirely by the invisible hand of gravity. But gravity, in its most extreme manifestations, doesn't just reshape, it can utterly destroy. Enter the Roche limit. This is a critical distance, a point of no return. If a celestial body held together only by its own gravity ventures inside this limit when orbiting a larger, more massive object, the tidal forces become stronger than the planet's own self-gravity. The consequence? Catastrophic disintegration. The planet is literally torn apart, ripped into millions of pieces, forming a spectacular, albeit tragic, ring system around its destroyer. We see this process at work in the debris disks around white dwarfs, the stellar remnants of sun-like stars. These dead stars have been observed with telltale signatures of heavy elements, suggesting they are polluted by the remains of rocky planets that ventured too close, met their demise, and were consumed. It's a cosmic shredder, reducing entire worlds to dust and pebbles. And what about the planets that survive but are stripped bare? Intense stellar radiation combined with relentless tidal forces can literally boil away a planet's atmosphere, leaving behind only its dense, rocky or metallic core. These are what we call Chthonian planets, named after the Greek chthonic deities of the underworld, because they are essentially the ghosts of gas giants. Imagine a world that was once a magnificent gas giant, perhaps even a beautiful ice giant like Neptune, now reduced to a barren, super-dense, exposed core perpetually blasted by its star. These are the ultimate survivors, yet transformed beyond recognition, offering us a glimpse into the skeletal remains of what were once majestic worlds. Their surfaces, if they have any, would be utterly alien, perhaps covered in exotic minerals forged under immense pressure and then exposed to the vacuum of space. But gravity's influence isn't always about pulling things closer. Sometimes it's about pushing them away violently. In the chaotic dance of young star systems, especially those with multiple massive planets or even multiple stars, close gravitational encounters can act like cosmic slingshots. A planet might get too close to a much larger sibling, experience a powerful gravitational kick, and be ejected from its home system entirely. These are the rogue planets, or nomad planets, cast adrift into the vast cold interstellar void. Imagine a world, perhaps even an Earth-sized one, hurtling through the darkness between stars billions of miles from any warmth or light. What would such a planet be like? Its surface would be an unimaginably cold, dark expanse, far colder than anything we experience on Earth. But here's where it gets truly fascinating. Even without a star, a rogue planet might not be entirely dead. If it's massive enough, its internal heat generated by radioactive decay within its core, or perhaps residual heat from its violent ejection and past tidal heating, could sustain a subsurface ocean of liquid water, much like the moons Europa or Enceladus in our own solar system. Such a world, far from the life-giving light of a star, could potentially harbour life in its hidden, warm, watery depths. It's a truly profound thought, isn't it? That life might not need a sun to thrive, but merely the internal warmth of a wandering world. And recent estimates suggest that there could be literally trillions of these rogue planets in our galaxy alone, far outnumbering the stars themselves. Each one a potential silent haven for life waiting to be discovered. Then there are the planets in binary or even multiple star systems, where the gravitational environment is a dizzying, ever-shifting ballet. Imagine a planet caught between 2 or 3 stars, each pulling it in different directions, its orbit a complex, looping path. The seasons on such a world wouldn't be dictated by a simple axial tilt, but by its erratic journey around multiple suns, leading to extreme temperature swings, unpredictable solar flares, and perhaps even periods of perpetual twilight or sudden, blinding bursts of light as different stars rise and set. These worlds are a testament to the fact that our neat, orderly solar system is just one of many possibilities, and often the universe prefers a more chaotic, gravitationally complex arrangement. So from worlds ripped apart and reduced to cosmic dust, to planets with perpetually molten surfaces, to those cast out into the eternal night, gravity is the master sculptor of the cosmos. It's a force that can both create and destroy, shaping worlds in ways that defy our earthbound intuition. The sheer variety of these gravitationally extreme planets reminds us that the universe is far stranger, far more diverse, and infinitely more awe-inspiring than we could ever imagine. And this is just the beginning of our journey into the truly unusual. Next time on Dreamy Science, we'll delve into worlds with truly exotic atmospheres, where the air itself might be made of rock vapour, where clouds rain down gemstones, or where the very sky is a kaleidoscope of alien chemicals. Prepare to have your mind blown once again, because when it comes to the universe, the only limit is our imagination, and even that often falls short. Welcome back to Dreamy Science, where we journey through the cosmos to uncover the universe's most astonishing secrets. Last time we marvelled at gravity's immense power, how it sculpts worlds into diamond behemoths, tears apart gas giants, and even flings planets into eternal stellar solitude. Gravity, we discovered, is the ultimate cosmic architect, but what about the very air that cloaks these incredible worlds? What about the invisible yet profoundly impactful realm of planetary atmospheres? You see, while gravity gives a planet its fundamental form, it's the atmosphere that truly dresses it, setting the stage for its character, its climate, and potentially its life. Our own Earth's atmosphere is a delicate, life-sustaining blanket of nitrogen and oxygen, perfect blend that allows us to breathe, regulates our temperature, and shields us from the harsh realities of space. But what if I told you that this familiar blue sky is just one tiny, improbable permutation in an infinite cosmic wardrobe? What if the universe's imagination for atmospheric chemistry stretches far beyond anything we can comfortably breathe or even comprehend? We're talking about worlds where the air itself is a bizarre cocktail of elements, where clouds aren't made of water and where rain can be anything from molten metal to glittering diamonds. So buckle up, because today we're plunging into the swirling, mind-bending diversity of exotic atmospheres, where the sky is truly the limit, or perhaps the beginning of the wonder. First, let's ground ourselves in a concept we're somewhat familiar with, the gas giants of our own solar system. Think of Jupiter, Saturn, Uranus, and Neptune. We understand them as colossal spheres of gas, primarily hydrogen and helium, swirling with immense storms and vibrant bands of colour. But gas here is a bit of a misnomer, isn't it? As you descend into Jupiter's crushing depths, the pressure becomes so intense that hydrogen, a gas on Earth, transforms into a liquid, then into an exotic, electrically conductive form known as metallic hydrogen. Imagine that, an ocean not of water but of liquid metal generated by sheer gravitational force swirling around a rocky core. The atmosphere of Baudupol isn't just air. It's a dynamic, multi-phase entity where familiar elements behave in utterly alien ways. The Great Red Spot, a storm larger than Earth, has raged for centuries, a testament to the sheer energy and scale of these atmospheric behemoths. These aren't just big planets, they are worlds where the very concept of a surface dissolves into an unfathomable gradient of pressure and temperature. Now let's crank up the heat. Imagine a world like WASP-12b, a hot Jupiter orbiting its star so closely that its year lasts just over an Earth day. These planets are gravitationally inflated by the intense stellar radiation, causing Herculean atmospheres to puff up to enormous sizes. Their day sides are scorching, reaching temperatures of thousands of degrees Fahrenheit. What kind of atmosphere could exist under such conditions? Well, for starters, it's not just hydrogen and helium. On these infernal worlds, even heavier elements can be vaporized. We're talking about atmospheres where iron, magnesium, and silicon are not just present in trace amounts, but exist as superheated gases. On WASP-76b, for instance, astronomers have detected iron vapor in its atmosphere. And because this planet is tidally locked, with one side perpetually facing its star and the other in eternal night, there's a dramatic temperature difference. The superheated iron vapor on the day side flows to the cooler night side, where it condenses. What happens then? It rains. Yes, it literally rains molten iron on WASP-76. Can you even begin to picture that? A sky full of incandescent metallic droplets falling onto a surface that is likely also molten or vaporized rock. It's a vision that both terrifies and enthralls us, a testament to the universe's capacity for extreme chemistry. But the exotic atmospheric menu doesn't end with metallic rain. Let's consider the chemical composition itself. Our own Venus offers a glimpse into a truly hellish atmosphere. A runaway greenhouse effect has trapped immense amounts of carbon dioxide, creating an atmosphere 90 times denser than Earth's, with surface temperatures hot enough to melt lead. And the clouds? Not water but sulfuric acid constantly raining down, only to evaporate before reaching the surface. It's a vision of what can happen when a planet's atmospheric chemistry goes terribly, terribly wrong for anything we'd recognize as life. Then there are worlds where sulfur itself plays a starring role. Picture a planet like Jupiter's moon Io, but scaled up to planetary proportions, racked by incessant volcanic eruptions. The atmosphere would be thick with sulfur dioxide, hydrogen sulfide, and other noxious volcanic gases perpetually shrouded in a toxic corrosive haze. The sky itself would be a perpetual sickly yellow-orange, raining down sulphurous compounds that would etch away any exposed surface. It's a world of perpetual chemical warfare, utterly inhospitable to Earth-like biology, yet brimming with its own unique violent beauty. Now let's journey to the frigid outer reaches, far from the warmth of the star. Here we encounter worlds like Saturn's moon Titan, a truly breathtaking example of an exotic atmosphere. Titan is the only moon in our solar system with a dense atmosphere, primarily nitrogen but with significant amounts of methane and other hydrocarbons. On Titan, methane isn't just a gas, it's a fluid that cycles through lakes, rivers, and even rainfall. Imagine standing on Titan's surface looking up at a sky where clouds are made of methane and precipitation falls as liquid natural gas. The landscape is carved by methane rivers and shorelines lap at methane lakes. It's a complete hydrological cycle, but with a chemistry that is utterly alien to our water-based experience. And within this complex, cold, organic, ritual atmosphere, scientists speculate about the potential for unique forms of life entirely different from our own. But what if the very ground beneath your feet becomes part of the atmosphere? On planets orbiting incredibly close to their stars, even closer than our hot Jupiters, the temperatures can reach such extremes that the surface rock itself begins to vaporize. Imagine a world where the crust boils, creating an atmosphere not of hydrogen, oxygen, or carbon dioxide, but of superheated rock vapor. We're talking about silicate and metal vapors swirling in the sky. As these mineral vapors rise and cool in the upper atmosphere, they would condense, forming clouds of tiny rock particles. And what happens when those clouds get heavy enough? It rains rock. Or perhaps, if the conditions are just right, it rains glass. Picture a perpetual, fine drizzle of molten silicates solidifying into tiny shards as they fall, only to re-vaporize upon hitting the scorching surface. It's a world where the distinction between land and sky blurs into an incandescent, mineral-rich haze. And speaking of precipitation, let's revisit the idea of diamond rain. We touched upon diamond planets in Chapter 1, but the atmospheric implications are equally astounding. On ice giants like Uranus and Neptune, scientists believe that extreme pressures deep within their atmospheres compress methane, turning it first into liquid hydrocarbons, then into solid diamonds that literally rain down into the planet's interior. Now, scale that up to a super-Neptune exoplanet with even higher pressures and more methane. You could have entire atmospheric layers where carbon, is continuously being forged into diamonds and precipitating downwards a ceaseless cosmic shear of precious gems. What about even more dazzling atmospheric phenomena? Some exoplanets, particularly those with silicate-rich atmospheres, might host clouds made of corundum, the mineral that forms rubies and sapphires. Imagine the sky where the clouds aren't white or grey but shimmer with deep reds and blues, potentially raining down tiny glittering sapphire or ruby particles. The very air around you could be infused with glittering dust, a cosmic jewel box in perpetual motion. And then there are worlds so hot, so irradiated by their stars that their atmospheres are not merely gaseous, but plasma. On these ultra-hot worlds, the gases are ionized, creating a glowing, electrically charged envelope that interacts violently with the stellar wind. The sky itself would be a dynamic display of auroras, arcs of electrical discharge, and an omnipresent, eerie glow, constantly being stripped away and replenished in a cosmic dance of energy. The universe, you see, is the master of atmospheric alchemy. It takes the fundamental building blocks, hydrogen, carbon, oxygen, nitrogen, silicates, metals, and through the crucible of gravity, temperature, and stellar radiation concocts environments that defy our wildest imaginings. These atmospheres are not static, they are dynamic, ever-changing systems. They are born from volcanic outgassing, stripped away by fierce stellar winds, replenished by impacts, or transformed by internal planetary processes. They are the breathing, swirling, protective or destructive envelopes of worlds across the cosmos. As we cast our telescopes across the vastness searching for signs of life, we often look for familiar atmospheric biosignatures, oxygen, methane, ozone. But what if life, in its boundless cosmic creativity, has found a way to thrive in methane lakes, sulphurous clouds, or even within the metallic mists of rock vapor worlds? What if the breath of alien life is a chemical signature we haven't even begun to anticipate? The study of exoplanet atmospheres is still in its infancy, yet it has already unveiled a gallery of wonders. From molten iron rain to diamond snow, from methane seas to skies of vaporized rock, these distant worlds challenge our intuition and expand our understanding of what's possible. They remind us that our Earth, with its mental blue sky and breathable air, is a precious anomaly, a cosmic miracle. But they also show us that the universe is infinitely inventive, a place where the most improbable and fantastical atmospheres are not just theoretical but real, waiting to be discovered. So what kind of exotic atmosphere would you most want to explore, even if just from a safe distance? Let me know in the comments or on social media using Dreamy Science Atmospheres. Next time we'll delve into the bizarre and beautiful worlds that orbit not one, but 2 or even 3 stars, where sunsets are a dazzling ballet of light and shadow. Until then, keep looking up and keep dreaming big. We've journeyed through diamond worlds, felt the immense tug of tidal forces, and gazed upon skies raining molten iron and even rubies. We've stretched our imaginations to encompass atmospheres spun from rock vapor and oceans of liquid methane. But what happens when the very source of light and life, the star itself, multiplies? What kind of worlds are forged in the gravitational crucible of not 1 but 2, 3, or even more suns? When we look up at our own sky, our single solitary sun seems like the cosmic norm. It's what we've always known, a stable anchor in our solar system. Yet statistically, our sun is a bit of an oddball. Most stars in our galaxy aren't solitary wanderers. They live in partnerships, in intricate ballets of gravity. Binary star systems, where 2 stars orbit each other, are incredibly common, making up perhaps half or more of all stellar systems. And beyond binaries, we find trinary, quaternary, and even higher-order multiples. This means that if planets are common, then planets with multiple suns are by extension also incredibly common. Imagine a sun. You see a single fiery orb descend below the horizon. painting the sky in hues of orange and purple. Now shatter that image. Picture two suns, one a brilliant yellow, the other a deep smouldering red, both dipping below a distant mountain range, casting long crisscrossing shadows. Or perhaps three suns, a celestial kaleidoscope, each tracing its own path across the firmament, bathing the landscape in an ever-shifting tapestry of light and colour. This isn't science fiction. This is the everyday reality for countless worlds across the universe. The gravitational dynamics in these multiple star systems are, to put it mildly, mind-bendingly complex. For a planet to exist in such a system, it must find a stable orbital path, a delicate balance amidst competing gravitational pulls. There are two primary configurations for planets in binary systems. First, we have Schwarz-type orbits, or circumstellar planets. Here, a planet orbits just one of the stars, with the other star or stars acting as a more distant but still significant gravitational influence. Think of it like our Earth orbiting the Sun, but with a second, smaller sun visible in the sky, sometimes closer, sometimes further away, pulling at our world, nudging its orbit, and adding its light to the day. For stability, the companion star usually needs to be far enough away that its gravitational tug doesn't rip the planet from its primary's embrace. These planets would experience relatively stable seasons based on their primary star, but with an additional, sometimes dramatic influx of light and heat from their stellar companion as it waxes and wanes in the sky. Second, there are P-type orbits or circumbinary planets. These are the true Tatooine worlds we often dream of, where a planet orbits both stars simultaneously. Instead of a single central star, the planet traces a wider path around the barycenter, the common center of mass of the two orbiting stars. This configuration is far more challenging for planetary formation and stability. The gravitational dance of the two stars can easily disrupt the delicate process of accretion in a protoplanetary disk, either flinging nascent planetesimals away or preventing them from ever coalescing. Yet we found them. Kepler-16b, the first confirmed circumbinary planet, orbits a K-type dwarf and a red dwarf. From its surface, you'd witness not one but two sunsets, a sight that truly puts our single-star perspective into cosmic context. The challenges for these worlds extend far beyond just the visual spectacle. Planetary formation itself is a high-stakes game. In binary systems, the gravitational stirring can be both a blessing and a curse. While it might disrupt the outer reaches of a protoplanetary disk, it can into stable zones, help to concentrate material, perhaps even speeding up the formation of planets. However, the odds of a planet being ejected from such a system are significantly higher. A gravitational slingshot from a close pass with a stellar companion could send a world careening into the cold, dark void of interstellar space, becoming one of those rogue planets we discussed earlier. Now let's talk about light and climate. On Earth, our climate is largely driven by the steady energy output of our Sun and the tilt of our planet's axis, which creates our seasons. On a world with multiple suns, this becomes astronomically more complex. The habitable zone, that sweet spot where temperatures allow for liquid water, isn't a static ring, it's a dynamic shifting region, morphing and pulsating as the stars themselves orbit each other. Imagine a planet in an S-type system where its primary star is a stable, sun-like star, but its companion is a highly eccentric red dwarf. For most of the year, the red dwarf might be a distant, faint ember in the sky, contributing little heat. But then it swings in close, its infrared radiation suddenly warming the planet, perhaps triggering rapid melting of polar scans or driving intense atmospheric convection. The year on such a world isn't just about its orbit around its primary, it's also about the super year of its primary and secondary star orbiting each other. Seasons could be dictated not just by axial tilt, but by the stellar dance itself, leading to periods of extreme heat and cold that dwarf anything we experience on Earth. For circumbinary planets, the situation is even more intricate. The planet orbits both stars, meaning its distance from the combined light source is constantly changing as the stars themselves revolve around each other. This could lead to wild temperature fluctuations over the course of its year. One moment, both stars might be on one side, beaming down their combined energy. The next, they might be on opposite sides or even eclipse each other from the planet's perspective, plunging the world into a brief, chilling darkness. This constant variability would exert immense pressure on any developing climate, demanding incredible resilience or novel atmospheric buffering mechanisms. Consider the spectrum of light. What if one star is a scorching blue-white giant, emitting intense ultraviolet radiation, while its companion is a cooler, dimmer red dwarf bathing the planet in infrared and deep red light? Photosynthesis, as we know it, relies on specific wavelengths of light. Life on such a world might evolve entirely new photosynthetic pigments, perhaps utilizing a broader spectrum of light or even adapting to intermittent bursts of different light types. Imagine plants with leaves that shift color throughout the day, optimizing their energy capture as different suns rise and set. And what about timekeeping? Our circadian rhythms are synced to a 24-hour cycle of light and dark. How would life evolve internal clocks on a world with their irregular days and nights, or where multiple suns rise and set at different intervals? Perhaps life would adapt to longer, more complex cycles, or rely on other environmental cues beyond light. The concept of day and night might become fluid, a kaleidoscope of multiple shadows and overlapping twilight zones. The extreme variability in energy input poses a profound challenge for the evolution of complex life. Stable conditions are often seen as a prerequisite for life to flourish and diversify. Yet the universe constantly challenges our assumptions. Perhaps life on these worlds would be primarily subsurface, insulated from the chaotic surface conditions. Or perhaps the intense selective pressures would drive the evolution of incredibly adaptable extremophiles, organisms capable of rapid metabolic shifts or even a form of suspended animation during periods of stellar flux. We might find organisms that thrive in wide temperature ranges, or those that can quickly migrate to more favorable zones as their stars dictate the climate. The implications for evolution are staggering. The constant, unpredictable changes in light, heat, and gravity would be a relentless forge, shaping species in ways we can barely comprehend. Could intelligence arise in such a chaotic environment, fostering a deep understanding of celestial mechanics and orbital prediction as a matter of survival? What kind of societies would form under skies where the very suns are engaged in an eternal dynamic dance? As we continue to observe the cosmos, our telescopes are revealing more and more of these multi-star planetary systems. Each discovery is a testament to the universe's boundless creativity, a reminder that our own solar system, with its single star and relatively stable orbits, is but one of an infinite number of possibilities. These worlds of shifting suns challenge our most fundamental assumptions about stability, habitability, and the very nature of time itself. They force us to expand our definition of what a day is, what a year means, and what conditions might truly foster life. We stand at the precipice of understanding, our minds grappling with the sheer scale and strangeness of these celestial ballets. The dreamy science of multiple suns invites us to imagine a symphony of light and shadow, a universe where the familiar concepts of sunrise and sunset are transformed into something utterly alien and profoundly beautiful. But what if a world isn't just dealing with multiple suns, but also with truly alien geology? What if the very ground beneath our feet is unlike anything we've ever encountered? Prepare yourselves, because our next stop takes us to worlds where the rocks themselves defy earthly logic, where the crust is a canvas for the universe's most bizarre geological wonders. We've soared through skies painted by multiple suns, felt the gravitational tug of cosmic dance partners, and even imagined the sting of molten metal rain. But now let's descend. Let's plant our feet, metaphorically speaking, on the solid or perhaps not so solid ground of these extraordinary worlds. Because as mind-bending as the atmospheres and orbital mechanics can be, what lies beneath the surface, the very geology of alien planets, can defy earthly logic in ways you might not even begin to imagine. You see, for us Earthlings, rock means silicates, quartz, feldspar, olivine. It means granite mountains and basaltic plains. But what if the fundamental building blocks are different? What if the pressures are so immense, the temperatures so extreme, or the chemical composition so utterly bizarre that the very definition of rock is rewritten? Welcome to the realm of alien geology, where the ground beneath your feet could be anything from shimmering diamond to solid metal, or even a shifting landscape of exotic ices. Let's start with a world we've already touched upon, but now we'll dig deeper, quite literally. Remember 55 Cancri, the diamond planet? We discussed how its carbon-rich beginnings, combined with immense pressure, could forge a world with a vast diamond mantle. But think about the geology of such a place. Imagine not just a diamond interior, but a surface where diamond isn't a rare gem, but a fundamental landscape feature. What would it be like to walk on mountains of crystalline carbon, perhaps eroded by the winds of superheated gas, leaving behind facets that catch the light of its binary suns? The very ground would shimmer, reflecting light in a way that would make any terrestrial geologist question their sanity. Here, rock isn't dull grey-brown, it's a spectrum of brilliance, a testament to carbon's incredible versatility under pressure. But carbon isn't the only element capable of forming landscapes beyond our wildest dreams. What about worlds dominated by metals? We know that planetary cores are typically metallic, but imagine a planet so thoroughly differentiated, or perhaps one that's a stripped-down core of a former gas giant. A Chthonian planet, as we discussed in Chapter 2, where the surface itself is molten or solid metal. Picture a landscape of iron and nickel, perhaps glistening under a distant star or slowly solidifying into vast metallic plains and towering crystalline structures. Walking on such a world would be like traversing a colossal oxidized smelting furnace where every step rings with the metal clang of an alien sound. The erosion patterns would be different, the way heat radiates would be unique, and the very concept of soil would be utterly foreign. Would magnetic fields be visible through metallic dust storms? What kind of life, if any, could etch a living from such a conductive, heavy landscape? Then we have the worlds where rock isn't even silicate or metal, but something far more ephemeral to our earthbound senses: ice. And I don't just mean water ice, though that alone can form incredible geological features on moons like Europa and Enceladus. We're talking about worlds where ammonia ice, methane ice, carbon dioxide ice, or even more exotic compounds like nitrogen ice form the bedrock. On these frigid outposts, what we call volcanism takes on a chilling new meaning. Cryovolcanism. Instead of molten silicate rock erupting from a fiery vent, imagine geysers of liquid nitrogen and ammonia or methane bursting forth from cracks in the icy crust. These icy lavas would flow across the surface, carving channels, building up bizarre translucent mountains, and forming vast frozen plains that shimmer with alien beauty. Think of Triton, Neptune's moon with its nitrogen geysers, or Pluto with its vast Sputnik planitia of nitrogen ice. Now scale that up to a full-fledged planet where ice tectonics might slowly grind and reshape the surface, creating rifts and mountain ranges composed not of rock but of frozen gases. The internal heat that drives this activity could come from radioactive decay, but more often it's the relentless kneading of tidal forces from a massive gas giant or a close-orbiting star. constantly stretching and squeezing the world, generating friction and heat within its icy mantle. The icebergs in their liquid oceans wouldn't be water, but solid ammonia or methane, floating in a sea of their own liquid form, perhaps denser, perhaps lighter, creating a truly alien hydrological cycle. And speaking of extreme conditions, let's revisit the ultra-hot worlds, where the very atmosphere is made of rock vapour, like those we explored in Chapter 3. What kind of geology emerges when silicates boil off the surface, condense into clouds, and then rain down as molten rock or fine glass particles? On the permanent night side of a tidally locked planet like K2141b, where temperatures plummet, those rock rains solidify rapidly, creating landscapes of obsidian-like glass or strange crystalline formations. Imagine walking on a planet where the ground is literally made of cooled lava from the sky, a continuously resurfaced world where glass mountains rise and fall, sculpted by corrosive atmospheric currents and the relentless cycle of vaporization and recondensation. This isn't just erosion, it's a constant geological rebirth, where the surface is perpetually being melted, vaporized and solidified anew. Consider also the sheer scale of pressure. On a super-Earth or mini-Neptune several times the mass of our homeworld, the pressures deep within the mantle could be so immense that familiar minerals transform into entirely new hyper-dense phases. Olivine, a common silicate on Earth, might metamorphose into exotic polymorphs like wadsleyite or ringwoodite or even denser structures we haven't yet discovered. These are not just theoretical curiosities, they're real mineral phases stable only under mind-bending pressures, altering the planet's density, its thermal conductivity, and even its seismic properties. A seismic wave passing through such a super-dense alien mantle would tell a story utterly unlike anything recorded on Earth. The very rock cycle would be different, with new minerals forming and breaking down under conditions that would vaporize our planet. And what about worlds where the constituent elements themselves are unusual? What if a planet forms in a star system unusually rich in heavy elements, perhaps from the remnants of a peculiar supernova? Could we find worlds where the dominant rock isn't silicon oxygen but perhaps tungsten, or even more exotic super-heavy elements? Imagine a planet with the surface of solid tungsten, one of the densest and most heat-resistant metals known. Walking on such a world would be like traversing a landscape of pure unyielding weight, reflecting light with a dull metallic sheen utterly alien to our silicate-based experience. The mountains would be impossibly robust, the valleys carved over eons by forces we can barely comprehend. Even the processes that shape geology would be different. Tidal forces, which we discussed in Chapter 2, aren't just for heating interiors. On some worlds, the sheer gravitational stresses could cause perpetual tidal tectonics, constantly pulling and pushing at the crust, creating a network of deep fissures and faults unlike any earthly plate boundary. Imagine a world where the ground is constantly groaning, stretching and cracking under the influence of a nearby gas giant, its surface a dynamic tapestry of shifting plates and erupting fissures, perpetually reshaped by the unseen hand of gravity. Earthquakes here wouldn't be isolated events. They might be a constant low-level tremor, the very heartbeat of a tidally stressed world. The beauty of alien geology lies in its utter defiance of expectation. It forces us to shed our Earth-centric biases, to open our minds to the idea that rock is a fluid concept dependent entirely on the cosmic ingredients and the extreme conditions of its formation. From crystalline carbon mountains to plains of solid metal, from cryovolcanic ice flows to constantly regenerating glass scapes, the universe offers an endless gallery of geological wonders. Each one challenges our understanding, expands our definition of what a planet can be, and reminds us that the most incredible landscapes are often the ones we haven't even conceived of yet. This journey into the heart of planetary geology leaves us with a profound sense of awe, doesn't it? It's a humbling reminder that our familiar world is just one of an infinite number of possibilities. But what happens when we combine these extreme geologies with the very essence of planetary life? What kind of organisms could possibly thrive on worlds of diamond, metal, or ice? That, my curious friends, is a question for our next cosmic adventure. We'll explore the truly mind-bending concept of alien biology, and how life, in its relentless ingenuity, might find a way to flourish in places we deem utterly uninhabitable. Are you ready to meet the ultimate survivors? I know I am. Make sure to follow Dreamy Science for all our upcoming episodes, and don't forget to share your favourite alien geology concept with us using Dreamy Science Geology. Until next time, keep looking up and keep dreaming big. Now, after journeying across diamond worlds, through molten iron rains and beneath the chaotic skies of multiple suns, we arrive at perhaps the most profound, most humbling, and most awe-inspiring question of all. What about life? For all our explorations of extreme geology, exotic atmospheres, and mind-bending orbital mechanics, the ultimate purpose of this cosmic tour is to expand our understanding of where and how life might exist beyond our pale blue dot. We've meticulously catalogued the universe's most unusual planets, not merely as scientific curiosities, but as potential cradles for biology utterly unlike our own. You see, our imaginations, as vast as they are still tethered to the familiar. We imagine life needing liquid water, a stable energy source from a star, and a narrow range of temperatures. But what if the universe, in its infinite creativity, has already far surpassed our wildest biological fantasies? Let's dismantle our Earth-centric biases, piece by painstaking piece, and truly open our minds to the boundless possibilities of the alien biology. We know life, as we understand it, is carbon-based, relies on liquid water as a solvent, and primarily derives energy from sunlight photosynthesis or chemical reactions chemosynthesis. But what if these aren't universal prerequisites? What if, across the cosmos, life has found entirely different answers to the fundamental challenges of existence? Imagine for a moment the foundational solvent for life. On Earth, it's water, a truly remarkable molecule with its polarity, high heat capacity, and ability to dissolve a vast array of compounds. But in the frigid outer reaches of a star system, or on a world with a radically different atmospheric composition, water might be a rare commodity, locked away as ice or vapour. Could liquid methane, like the rivers and lakes we've discussed on Titan, serve as a solvent for an entirely different biochemistry? Methane is nonpolar, meaning it would support a very different set of chemical reactions, potentially involving lipids, waxes, and nonpolar organic molecules. Or what about liquid ammonia, found on worlds far colder than Titan, offering its own unique solvent properties? Even more extreme here, consider sulfuric acid, as on Venus. While incredibly corrosive to Earth life, could organisms evolve to thrive in such an environment using acid as their very lifeblood? Perhaps even supercritical fluids existing at temperatures and pressures above their critical points could host exotic chemistries acting as both solvent and reactant. Then there's the question of energy. Our sun is a glorious, life-giving furnace, but not all worlds bask in its direct glow. We've explored rogue planets, cast adrift from their parent stars, traversing the interstellar void in perpetual darkness. Yet could life persist there? Absolutely. We already know about chemosynthesis on Earth, where organisms thrive around hydrothermal vents, drawing energy from chemical gradients released by geological activity. On a rogue planet, intense internal heating driven by residual formation energy or radioactive decay could power similar ecosystems beneath a thick ice shell within a subsurface ocean. Tidal forces, as we saw with Io, are another powerful energy source. A planet caught in a gravitational tug-of-war could generate enough internal heat to sustain liquid water, or even exotic cryomagma. powering life through tidal tectonics and associated chemical reaction. And what about the very building blocks of life? Carbon is famously versatile, forming long stable chains and rings, but it's not the only element capable of complex chemistry. Could silicon, which shares some chemical similarities with carbon and is far more abundant in rocky planets, form the backbone of alien life? Silicon-based life might thrive at much higher temperatures, perhaps even on worlds where carbon compounds would simply vaporize. Imagine organisms with crystalline structures, metabolizing silicates and breathing in volatile compounds from a superheated atmosphere. Or perhaps boron, sulfur, or even phosphorus could play more central roles in biologies that defy our carbon-centric expectations. Let's revisit some of the extreme worlds we've encountered and imagine the life forms they might harbour. On diamond planets like 55 Cancri, where unimaginable pressures crush carbon into crystalline forms, could life exist not on the surface but deep within the mantle? Perhaps extremophiles that incorporate diamond into their very structures, thriving on geochemical energy from the planet's core, existing in pockets of superheated high-pressure fluids, or even navigating networks of subterranean diamond caves. Their bodies might be incredibly dense, their metabolism slow, their lives measured in eons rather than years. Consider the tidally locked worlds we discussed, perpetually facing their star on one side and the eternal night on the other. Life here would be a testament to adaptation. On the scorching day side, organisms might have reflective surfaces, burrow deep, or evolve to be dormant during the intense stellar glare, emerging only at the terminator line. On the frigid night side, life might cluster around geothermal vents or utilize infrared radiation from the planet's interior. The twilight zone, that narrow band of perpetual dawn or dusk, could be a thriving ecosystem with organisms adapted to constant fierce winds, perhaps even using them for locomotion or to generate energy like vast biological windmills. Their bodies might be streamlined, anchored deep, or even migratory, following the slow drift of the twilight zone. What about the Chthonian planets, the stripped cores of former gas giants? These worlds are essentially bare, hot, metallic hearts. Could life exist on such a planet, perhaps metabolizing the heavy metals themselves, thriving in superheated metallic oceans or within cracks in a constantly shifting metallic crust? Imagine organisms that breathe metallic vapors or absorb metallic ions directly from their environment, their bodies perhaps composed of crystalline metal alloys. And the rogue planets, those silent wanderers. We touched upon subsurface oceans, but let's truly embrace the implications. Deep beneath kilometers of ice, warmed by geothermal vents, entire ecosystems could flourish, powered by chemosynthesis. These would be worlds of perpetual darkness, where bioluminescence might be the primary form of communication and navigation. Life here would be slow, perhaps simple, but undeniably resilient, proving that a star is not always a prerequisite for life's spark. Our journey through exotic atmospheres also opens doors to truly bizarre biologies. On worlds like WASP-76b, with its molten iron rain, surface life seems impossible. But what about life in the atmosphere itself? Perhaps in cooler, higher layers where complex chemistry can occur, or even organisms that could tolerate or even utilize metallic compounds. We're talking about life forms that might literally etch metal vapor or incorporate exotic elements into their biological machinery. On a Titan-like worlds, with methane lakes and rain, we can envision methanogens, organisms that metabolize methane, perhaps with cell membranes made of complex hydrocarbons, and a life cycle tied to the planet's methane hydrological cycle, a truly alien analogy to Earth's water-based ecosystems. Even the glasscapes and metallic surfaces of Chapter 5 present opportunities. On a world where rock vaporizes and rains down as molten glass, life might be transient, existing in cooler atmospheric layers or deep underground, only to emerge during periods of relative calm. Or perhaps life could evolve to rapidly colonize and exploit the freshly formed glass, incorporating silicates into their structure. Imagine organisms with exoskeletons of natural glass refracting light in dazzling alien patterns. The Versailles cryovolcanic ice worlds, with their exotic ices of methane, nitrogen, or ammonia, point again to subsurface oceans, but perhaps also to life forms that directly metabolize these cryocompounds. Could there be organisms that thrive in liquid nitrogen, or whose cellular processes depend on the extreme cold? And what about our multiple star system? Life on a circumbinary planet like Kepler-16b would contend with wildly fluctuating temperatures and light cycles. Organisms might evolve complex circadian rhythms synchronized to multiple stellar periods, or possess adaptive pigments that can efficiently absorb light from different star types, perhaps a red dwarf and a yellow sun, leading to a kaleidoscope of biological colors. We are pushing the boundaries of what life even means. Could there be life forms that exist as pure energy or as complex patterns within a plasma? Could there be non-biological intelligences arising from the complex interplay of cosmic forces? These are questions that stretch beyond our current scientific grasp, but they are questions that the vastness and strangeness of the universe compel us to ask. The habitable zone isn't just a narrow band around a star where liquid water can exist on the surface. It's a concept that needs radical expansion. It includes subsurface oceans warmed by tidal forces, atmospheres that shield against radiation, and exotic chemistries that open up entirely new pathways for biological evolution. It includes planets where life might thrive on geothermal heat, chemical gradients, or even the sheer energy of a planet's rotation. Our journey through these most unusual planets has been a humbling experience. It has shown us that our understanding of what is normal is profoundly limited by our single data point, Earth. The universe is not merely stranger than we imagine, it is stranger than we can imagine. And that, my friends, is the most exciting scientific truth of all. It means that somewhere out there, life is flourishing in ways we haven't even begun to conceive, challenging every assumption we hold dear. It's a universe teeming with possibilities, waiting for us to expand our minds enough to truly see it. What do you think is the most mind-blowing possibility for alien life? Share your wildest theories with us. Use dreamy science and let your imagination soar. We're just scratching the surface of cosmic biology, and the greatest discoveries, I believe, are yet to come. We've journeyed through diamond planets and worlds of molten iron rain, through realms sculpted by titanic tidal forces and atmospheres of rock vapor. We've faced the dazzling chaos of multiple suns and the bewildering geology of non-silicate worlds. Each stop on our dreamy science tour has chipped away at our Earth-centric biases, forcing us to stretch our imaginations to truly grasp the universe's boundless creativity. But now we arrive at perhaps the most profound, most mind-bending frontier of all, alien biology. We've already begun to dismantle our comfortable assumptions about life, haven't we? We've questioned the absolute necessity of liquid water, of carbon as the sole building block, of sunlight as the only energy source. We've speculated about life clinging to the undersides of rogue planets, warmed by geothermal vents, or methane-based organisms swimming in frigid hydrocarbon seas. But what if we push past even those expanded horizons? What if we truly let go of our terrestrial definitions and embrace the full, unfathomable spectrum of what life could mean? Think about it. What is life at its most fundamental? It's a self-sustaining chemical system capable of Darwinian evolution. That's a pretty broad definition, isn't it? It doesn't specify carbon. It doesn't demand water. It simply requires a system that can take in energy, organize itself, replicate, and adapt. And when you liberate yourself from Earth's specific recipe, the possibilities explode into a dazzling, nearly infinite array. Let's revisit those alternative solvents, not just as exotic liquids, but as the very blood of alien ecosystems. Imagine worlds where liquid methane isn't just a solvent but a vital metabolic medium. On a place like Titan, with its frigid temperatures and thick nitrogen-methane atmosphere, perhaps life could utilize acetylene as an energy source, reacting it with hydrogen to release energy, much like we use glucose and oxygen. Their cells might be encased in lipid-like membranes formed from hydrocarbons, maintaining their internal chemistry against the external environment. Their biology would be slow, deliberate, unfolding over geological timescales, a dance of chemistry utterly alien to our rapid aqueous world. What would their equivalent of a tree look like, drawing energy from the hydrocarbon rain, its roots delving into icy soil for vital minerals? What kind of creature would stalk the methane shores, perhaps absorbing gases directly from the atmosphere, its body a complex matrix of organic polymers designed for the deep cold? Or consider the scorching acidic realms we discussed earlier, planets where sulfuric acid clouds perpetually shroud the surface. Here, life might thrive in a medium that would dissolve us in an instant. Perhaps these organisms are silicon-based, their robust molecular structures better suited to acidic conditions and higher temperatures. Their metabolism might involve complex redox reactions with sulfur compounds, extracting energy from this planet's turbulent chemistry. Their equivalent of photosynthesis might harness the intense infrared radiation permeating the lower atmosphere, or they might be chemosynthetic, drawing energy from the volcanic vents that spew sulfurous gases. We talk about extremophiles on Earth, organisms that thrive in acid, but imagine an entire biosphere built around it, where acid is not a threat but the very essence of existence. Their skin might be a highly resistant, perhaps crystalline material, their internal machinery a complex interplay of acid-stable enzymes and structural proteins. And what about silicon? We, carbon-based life forms, are built on carbon's incredible versatility, its ability to form four stable bonds, creating long complex chains and ring. Silicon, directly below carbon on the periodic table, shares some of these properties, but with crucial differences. Silicon bonds are stronger, requiring more energy to form and break, suggesting silicon-based life might operate at much higher temperatures, perhaps on worlds with molten surfaces or within volcanic vents. Imagine beings whose very structure is akin to silicate minerals, whose bones are like quartz, whose flesh is a complex high-temperature polymer. Their equivalent of water might be molten salts or even liquid silicates, slowly flowing through their crystalline bodies, facilitating their sluggish yet incredibly resilient metabolism. Their breathing might involve the slow exchange of oxygen or sulfur compounds at extreme temperatures. This isn't just a thought experiment. It's a profound challenge to our intuitive understanding of what constitutes a living being. But the energy sources, they're just as crucial as the building blocks and the solvents. We Earthlings are largely solar-powered, directly or indirectly. But what about worlds perpetually shrouded in darkness, or those deep within interstellar space? We've touched on chemosynthesis, but let's expand it. Imagine life forms that draw energy not from light, but from the very fabric of space-time distortion, from the immense gravitational gradients near a black hole, or from the intense magnetic fields of a neutron star. Perhaps they don't metabolize chemicals in the way we understand, but rather states of matter. Consider the Chthonian planets, those stripped cores of gas giants. Deep within their metallic mantles, under pressures that would crush any known earthly material, could there be life? Life composed of hyper-dense matter, perhaps even degenerate matter, operating on principles we can barely conceive. Their metabolism might involve the slow rearrangement of metallic hydrogen or the harvesting of energy from the shear pressure gradients. Their existence would be measured in eons, their movements imperceptible to our senses, yet they would be alive, evolving, adapting to their impossible environment. And what about radiation? We tend to view radiation as a destructive force, a bringer of mutations and death. But could life, over billions of years, evolve to utilize it? Imagine organisms on planets orbiting pulsars bathed in intense, regular bursts of X-rays and gamma rays. Perhaps their cellular machinery is designed not to shield from this energy, but to capture it, to harness it directly for metabolic processes. Their skin might be a dense metallic shield, their internal chemistry a cascade of high-energy reactions, constantly repairing and rebuilding itself under conditions that were instantly lethal to us. Their perception of the universe might be entirely based on electromagnetic frequencies, seeing the cosmos as a symphony of radiation. The concept of life itself might need a fundamental redefinition in the face of such diversity. What if life isn't necessarily cellular? What if it's a collective intelligence spread across a planetary crust, a vast network of interconnected fungi-like structures communicating through chemical signals or electrical impulses? What if it's a pattern of energy, a self-organizing plasma phenomenon in the atmosphere of a gas giant, constantly forming, dissolving and reforming, carrying information across generations? And then there's the question of perception and intelligence. If life evolves in a methane ocean, how does it see? Perhaps through sonar-like pulses, navigating by echoes in the frigid liquid. If it lives deep within a planet's crust, how does it hear or feel? Through seismic vibrations, detecting the subtle tremors of the world around it. Our senses are finely tuned to Earth-specific conditions. Alien senses will be equally specialized, leading to perceptions of reality so vastly different from our own that we might not even recognize them as such. What kind of consciousness, what kind of intelligence would emerge from such radically different sensory inputs and biological structures? It might not be anything like our notions of individual minds. It could be something distributed, emergent, or even entirely non-biological and abstract. This is the ultimate humbling journey, isn't it? Every time we think we've grasped the boundary of the possible, the universe laughs and shows us something even stranger. The habitable zone isn't a narrow band around a star. It's a conceptual space that encompasses an unimaginable array of chemical, thermal, and energetic conditions. Life, in its cosmic extravagance, might be everywhere, taking forms that defy our wildest dreams and most elaborate scientific models. So, as we conclude this chapter on alien biology, I invite you to keep questioning, keep dreaming. The next time you look up at the night sky, don't just see distant stars and planets. See the infinite possibilities they hold, the countless ways that life might have found a foothold, thriving in environments we once thought utterly barren. The universe is telling us a story, a grand narrative of improbable existence, and we're only just beginning to learn its language. What do you think alien life might look like? Share your own dreamy science theories with us online. Let's expand our collective imagination even further. Because the most unusual planets in the universe are not just those with their exotic geology or bizarre atmospheres, they are those that host the truly unusual, the truly alien, the truly alive. You've journeyed with us through worlds of diamond and metal, through skies of molten iron and seas of liquid methane. We've stretched the very definition of a planet to include rogue wanderers and Chthonian cores. And in our last exploration, we dared to imagine life itself, not as a carbon copy of Earth, but as an infinite tapestry woven from the universe's most exotic threads. We asked, what kind of life could thrive in methane lakes, sulphurous clouds, or within metallic mists? What does life truly mean beyond our Earth-centric definitions? These aren't just rhetorical questions for our dreamy science audience. They are the frontier of astrobiology, the very edge of our understanding. Because if we've learned anything on this cosmic expedition, it's that the universe is far more imaginative than we are. And that means the definition of life itself might be one of our most profound human limitations. Think about it. Our entire search for extraterrestrial life for decades has been predicated on the idea of the habitable zone, that Goldilocks band around a star where temperatures allow for liquid water. It's a foundational concept, and for good reason. Water is a phenomenal solvent, essential for Earth life and abundant in the cosmos. But what if we've been looking through too narrow a keyhole? What if our very definition of habitable is hopelessly provincial? Imagine a planet ejected from its star system, now a rogue wanderer hurtling through the interstellar void. On its surface, temperatures plunge to absolute zero. A desolate frozen rock, right? Uninhabitable. Yet, as we've discussed, deep within its icy mantle, sustained by the primordial heat of its formation and the constant squeeze of tidal forces from its own core, an ocean of liquid water could persist. A subsurface ocean, warmed by geothermal vents shielded from cosmic radiation, potentially teeming with chemosynthetic life. Is this not a habitable zone? It's just not the one we typically envision, a surface world bathed in stellar light. Or consider the gas giants, those colossal worlds we tend to dismiss as too hostile. We picture swirling, crushing atmospheres, unfathomable pressures and exotic chemistry. But what if within certain layers of their atmospheres, where conditions are just right, not too hot, not too cold, not too dense, a form of aerial, buoyant life could exist? Perhaps gas bag organisms like cosmic jellyfish, drifting on atmospheric currents, metabolizing exotic chemicals, and even reproducing in a vast three-dimensional ocean of gas. We're talking about a habitable zone that's a layer in a planet's atmosphere, not a surface. A dynamic, ever-shifting ecosystem floating on currents of metallic hydrogen or supercritical fluids. The universe, you see, laughs at our neat little boxes. It tells us that habitability isn't a fixed address, it's a condition. And those conditions can arise in an astonishing array of environments. We've talked about liquid methane on Titan, a solvent that behaves much like water at cryogenic temperatures. Could life evolve to utilize methane as its lifeblood, its metabolic medium? What about liquid ammonia, or even sulfuric acid, as on Venus? Could organisms develop robust protective membranes, perhaps silicon-based, to thrive in such corrosive environments? The possibilities, once you liberate your mind from Earth-centric assumptions, are truly mind-bending. This leads us to a fascinating and perhaps unsettling question. What if life doesn't even need traditional organic chemistry? What if the universe's creative spark extends to entirely different fundamental building blocks? We are carbon-based, water-dependent creatures, but silicon, for instance, shares many chemical properties with carbon. It can form long, complex chains and rings, albeit with different stability and reactivity. Could silicon-based life exist, perhaps in hotter, drier environments where carbon compounds might break down? Imagine crystalline organisms slow-moving, perhaps metabolizing silicates, building their structures from the very rocks they inhabit, living out geologic epochs. And what about energy? Our life thrives on sunlight or chemical gradients derived from it. But we've seen worlds where tidal heating provides immense energy, or rogue planets where geothermal vents are the only source. What if life could harness magnetic fields, or even the subtle distortions of space-time around massive objects? What if, in a truly exotic scenario, life could exist as self-organizing plasma, a complex dynamic pattern of ionized gas far removed from anything we recognize as biological? These are not science fiction fantasies. They are speculative scientific inquiries born from the very extremes we've explored and the fundamental laws of physics. The challenge, then, becomes immense. How do we detect such radically different forms of life? Our current biosignatures, oxygen, methane, water vapor, are all indicators of Earth-like biology. If life on a distant exoplanet uses a different solvent, a different energy source, or entirely different building blocks, its biosignatures might be utterly alien to us. We might be looking directly at a vibrant, thriving ecosystem and simply not recognize it. We need to broaden our search to develop new instruments and theoretical frameworks that can identify technosignatures, signs of technology, or agnostic biosignatures, indicators of complex, ordered processes that are unlikely to arise purely from geology or atmospheric physics. Imagine detecting an unexplained energy imbalance in a planetary atmosphere, far beyond what stellar radiation or internal heat sources could account for. Or perhaps a planet whose surface features display intricate, non-random geometric patterns that defy geological explanation, hinting at a grand, engineered purpose. We might look for unusual spectral absorption lines in an atmosphere, indicative of complex, non-equilibrium chemistry that points to active metabolism, even if the compounds themselves are utterly alien. It's like trying to find a needle in a haystack when you don't even know what a needle looks like, or if it's even made of metal, or if it's even a needle at all, but perhaps a highly ordered, self-replicating crystalline structure. And if we somehow manage to detect it, what then? The true mind-bender is the concept of alien intelligence. If basic life can be so varied, imagine the diversity of consciousness. What would it be like to communicate with a being that perceives reality through seismic vibrations or electromagnetic fields, or that exists as a distributed intelligence across an entire planetary network? Their understanding of time, space, and even self might be so fundamentally different that our very concept of communication would need to be rewritten. How do you explain love or art to a silicon-based entity that experiences millennia as we experience days, or to a plasma being that exists as a wave of thought across a stellar corona? This brings us inevitably to the Fermi paradox. Where is everybody? If the universe is so vast and the conditions for life so diverse and widespread, why haven't we encountered definitive proof of other intelligent civilizations? This question, amplified by our journey through the truly unusual planets, becomes even more poignant. There are, of course, many proposed solutions. Perhaps the Great Filter is ahead of us, some catastrophic hurdle that almost all civilizations fail to overcome, like self-destruction through advanced weaponry, irreversible climate change, or an inability to escape their home system before a stellar catastrophe. Or perhaps the filter is behind us. The emergence of complex multicellular life, or even simple life, is far rarer than we imagine, making Earth an exceptionally lucky anomaly, a cosmic lottery winner against unfathomable odds. Another intriguing possibility is that advanced civilizations simply transcend physical existence, moving into digital realms or entirely different dimensions, becoming unacceptable to us. They might not communicate via radio waves, but through quantum entanglement or gravitational manipulation, methods we are only beginning to theorize. But what if the answer lies in our own limited perception? What if other intelligences are so alien, so utterly different from us, that we simply don't recognize them? They might not build radio telescopes or megastructures visible across light years. They might exist in forms we can't detect or communicate in ways we can't comprehend. Perhaps they inhabit regions of the universe we consider uninhabitable, thriving in the crushing depths of gas giants or within the hearts of stars, or even as intricate patterns within the quantum foam of space-time itself. The universe might be teeming with life and intelligence, a grand unseen chorus of existence, and we are simply deaf to its song. This journey through the most unusual planets is more than just a tour of cosmic oddities. It's an invitation to expand our minds, to question our assumptions, and to embrace the humbling realization that our anthropocentric view of the universe is just that, a single tiny perspective. The universe is not obligated to conform to our expectations, nor is life obligated to resemble us. Instead, we are presented with a canvas of infinite possibility, a testament to the universe's boundless creativity. We are reminded that every star, every planet, every moon holds the potential for something truly extraordinary. And in contemplating these dreamy scientific possibilities, we don't just learn about the cosmos, we learn about ourselves. We learn about our capacity for wonder, our drive for discovery, and our profound desire to connect with something larger than ourselves. So as we bring this exploration of the unusual to a close, remember this: the universe is under no obligation to make sense to you. But you, dear explorer, are under an obligation to keep questioning, to keep dreaming, and to keep looking. Because out there in the vast, bewildering, beautiful darkness, something truly unimaginable is waiting to be discovered. And it might just redefine everything you thought you knew. What are your wildest theories about alien life? What form do you think the next great discovery will take? Share your thoughts with us using our dreamy science on social media. We love hearing how these cosmic journeys expand your mind. The silence of the cosmos, that profound, echoing void we discussed, isn't necessarily an absence. What if it's a presence so vast, so utterly other, that our current instruments, our very human imaginations, simply aren't equipped to perceive it? What if the universe isn't just a canvas of natural wonders, but a grand workshop meticulously crafted by intelligences far beyond our comprehension? We've explored planets shaped by titanic forces, by exotic chemistry, by the relentless dance of stars. But what if the most unusual planets aren't born, but built? Imagine for a moment a civilization that has transcended the need for a single naturally occurring world. A civilization that has mastered its star, not merely orbiting it, but enveloping it. We're talking about structures on a scale that beggars belief, an ambition so audacious it redefines what it means to be a planet or a home. We're talking about megastructures. Consider the Dyson sphere. The very name conjures images of science fiction, but the underlying concept is rooted in pure physics and the relentless march of technological advancement. Picture your sun, our own glorious soul, pouring out an unimaginable torrent of energy every second. Only a minuscule fraction of that energy ever reaches Earth. Now what if an advanced civilization sought to capture all of it? Not just a sliver, but every single photon, every particle of stellar wind. A true Dyson sphere wouldn't necessarily be a solid, impenetrable shell. That would be incredibly unstable, prone to catastrophic impacts, and astronomically difficult to construct. Instead, envision a Dyson swarm, a vast intricate network of countless solar collectors, habitats and industrial complexes, all orbiting their star in a dense organized cloud. Each individual component is a world unto itself, a perfectly engineered environment absorbing every watt of the star's output. From a distance, this swarm might appear as a slightly dimmer, oddly shaped star, or perhaps an infrared glow unlike anything nature produces. Think about the sheer scale. Our sun is a powerhouse radiating 3.8 per 10 to 6 watts of energy. To harness even a significant fraction of that means building structures that would dwarf our entire solar system. These wouldn't just be power stations, they would be the foundations of entire civilizations. Imagine habitats suspended in the vacuum, each one a self-contained ecosystem, perhaps housing billions, even trillions of beings. These aren't just planets, they are engineered biospheres, meticulously designed and controlled. The surface of the world is not a crust of rock, but a mosaic of technology and artificial landscapes, constantly maintained, endlessly expanding. How would we detect such a marvel? If a Dyson swarm completely encloses its star, it would absorb most of the star's visible light, re-radiating that energy as in the infrared. infrared spectrum. So while we might not see a bright star, we might detect an unusually strong infrared signature from a region of space where we expect to see a star. It's a tantalizing prospect, a whisper from the void suggesting that the silence isn't empty, but merely re-engineered. But let's push this concept even further. What if a civilization, having mastered its star's energy, then sought to master thought itself? Enter the Matryoshka brain. If a Dyson swarm is about power, a Matryoshka brain is about computation on a cosmic scale. Imagine a series of nested Dyson spheres. The innermost shell captures the star's raw energy, but instead of just using it for habitat, it powers an immense supercomputer. The waste heat from that computer is then captured by a slightly larger outer Dyson sphere, which in turn powers an even larger, cooler supercomputer. This process continues layer after layer, each shell harnessing the waste heat of the one within it, until you have a colossal nested system of computational power that could simulate entire universes, process information at speeds we can barely conceive, and perhaps even host the collective consciousness of an entire civilization. This isn't just a planet, it's a cosmic mind. It's a world built not for physical habitation in the traditional sense, but for the expansion of intellect, for the eternal exploration of ideas. The life within such a structure might be purely digital, an emergent consciousness woven from countless processes, perhaps achieving a form of immortality by uploading their very minds into this grand artificial brain. The atmosphere would be currents of theatre, the geology would be layers of circuitry, and the weather would be fluctuations in processing power. To us, it might register as an incredibly complex non-natural heat signature, a thermal echo of alien thought. And these aren't the only possibilities. The universe, in its boundless capacity for the surprise, might also host ring worlds, Kishima's colossal bands of material, hundreds of millions of miles in circumference, rotating to create artificial gravity, with landscapes and oceans on their inner surfaces. Imagine a ribbon of habitable land, perhaps 1,000,000 miles wide, curving endlessly into the sky, lit by artificial suns or directed stellar light. These are not planets in the sense of a sphere of rock, but like planar worlds, vast ribbons of engineered paradise or industrial might. Or consider O'Neill cylinders, enormous rotating space habitats, miles long and wide, creating artificial gravity and containing entire ecosystems within their interiors, often nestled in vast fleets around a star, forming their own artificial planetary system. These are micro-worlds, self-contained ecologies sustained by deliberate design. What does it mean for a planet to be crafted? It means that its very existence is an act of intention, a testament to intelligence. These aren't just rocks and gas, they are monuments to ambition. Structures that blur the lines between technology, biology, and even philosophy. Could these megastructures be considered alive in some sense? If a Matryoshka brain hosts the collective consciousness of a civilization constantly evolving, processing, and adapting, isn't that a form of life, albeit one vastly different from our own? If a Dyson swarm is self-repairing, self-replicating, growing with the needs of its inhabitants, doesn't it exhibit characteristics we associate with biological systems? We are challenged, once again, to shed our Earth-centric definitions and open our minds to the truly alien. The ultimate irony, perhaps, is that these structures, designed to maximize efficiency and intelligence, might be inherently difficult for us to detect. Their purpose might be so alien to our own, their operations so subtle or so vast, that we simply don't recognize them for what they are. Perhaps they operate on energy scales or within dimensions we cannot yet perceive. Perhaps their signal is not a burst of radio waves, but the slow, inexorable reshaping of entire star systems, a process that unfolds over millennia, leaving traces that we, with our fleeting lifespans and limited perspectives, simply interpret as natural cosmic phenomena. This takes us back to the Fermi paradox with a fresh, awe-inspiring perspective. The great filter might not be a destructive force we have yet to face, but a transcendent ambition we have yet to grasp. Perhaps advanced civilizations don't seek to spread across countless natural planets, but to consolidate their existence into these magnificent, self-contained and self-sustaining artificial worlds. They might not be broadcasting their presence because they are too busy being their presence, existing on a plane of existence so advanced that our signals are like whispers in a hurricane, or their structures are simply too vast and too alien for our pattern recognition. So when you gaze up at the night sky past the familiar twinkle of stars, past the faint smudge of nebulae, consider this. What if some of those stars aren't natural celestial bodies at all? What if they are the shimmering, engineered surfaces of a Dyson swarm, the cool, silent hum of a matryoshka brain, or the impossibly vast arc of a ringworld? What if we are looking at the architecture of alien minds, not just the random creations of the cosmos? The universe, as we've seen, is a master of creation, crafting worlds of diamond, fire, and ice. But what if it also serves as the ultimate canvas for creation? A boundless realm where intelligence doesn't just adapt to planets, but builds them. This thought, I believe, is one of the most profound and humbling we can entertain, reminding us that the boundaries of what is possible are not set by our current understanding, but by the boundless creativity of existence itself, both natural and intelligent. The search for unusual planets, then, expands beyond the naturally occurring to the deliberately constructed, the intelligently designed. It demands that we not only sharpen our telescopes, but also broaden our imaginations, preparing ourselves for the ultimate reveal that the universe is not just filled with wonders, but with wonders crafted by hands we can only dream of. What are your thoughts on these cosmic constructions? Do you think we'll ever find a Dyson sphere, or are these concepts just too far beyond our reach? Share your ideas using dreamy science, and let's explore the infinite possibilities together. So you've imagined the Dyson swarm, a colossal network of collectors enveloping a star, drinking in its every photon. You've stretched your mind further to the matryoshka brain, nested layers of computational power, universe-scale supercomputer. Picture it, not a single solid sphere, but a shimmering, intricate lattice of quadrillions of solar collectors, each one a jewel reflecting a fraction of the star's fiery heart, all humming with silent purpose. Then, beyond that, within its embrace, the matryoshka brain itself, perhaps not a visible structure at all, but a gravitational anomaly, a region of space-time subtly warped by the sheer mass of its processing core, or a nested series of energy fields, each layer processing information at speeds beyond our comprehension. Its surface, if it could even be said to have one, would be a blur of unimaginable complexity, a cosmic fractal of pure thought. But what does it mean for a civilization to build such a thing? What is the purpose behind transforming a star system into a processing unit, a cosmic mind? We're not just talking about survival here, not merely about energy efficiency. We're talking about a profound shift in existence, a transcendence. Imagine a civilization that has solved its energy crisis, conquered disease, and even perhaps mortality. They would have reached a plateau of material comfort and biological security that we can only dream of. What then? What drives a species when the basic struggles for existence are eliminated? The initial euphoria of boundless energy and eternal life would eventually settle, giving way to a new kind of existential inquiry. The next frontier might not be outward expansion across the galaxy and starships laden with colonists and terraforming equipment, but inward, into the realm of information, computation, and simulated reality. What wonders could we create? What truths could we uncover if we had infinite processing power? A collective thought might have rippled through their nascent planetary network, sparking the ambition that would redefine their very being. Consider the ultimate unusual planet. Is it a world of diamonds or molten iron rain or cryovolcanoes? Or is it something far more abstract or far more engineered? When a civilization constructs a matryoshka brain, they are in essence creating their own planetary-scale habitat, a self-contained universe of thought and experience. Their world becomes the data streams, the simulated environments, the collective consciousness housed within layers of processing substrate. They are no longer bound by the physical surface of a single planet, or even the solid structures of a space habitat, but by the computational capacity they can harness. Imagine existing as pure information, a stream of consciousness flowing through vast, intricate networks of thought. Your sister could be anything you desire. Your environment, says Simon, a perfectly rendered reality, or a swirling abstract landscape of pure data. The sun, once a distant light source, now becomes the very engine of your being, its energy fueling every thought, every sensation, every simulated breath. To be truly free, they might have mused, is to be unbound by the arbitrary limitations of physical form, yet to possess all the richness of experience. For such an intelligence, the universe might become a canvas for thought, a resource for processing power. Their very existence could be a continuous evolving simulation, a quest for ultimate knowledge, or even the creation of entirely new artificial realities. Perhaps they live out eons within these simulated worlds, exploring every permutation of physics, philosophy, and experience, creating new forms of life within their digital confines. They might simulate entire galaxies running billions of years of cosmic evolution in mere moments, searching for patterns, for meaning, for the ultimate laws of existence. They could create sentient digital beings, entire civilizations born and evolved within their matrices, each one a grand experiment in consciousness, ethics, and societal development. The boundaries of reality would blur, their godhood over these inner universes unquestioned, their pursuit of knowledge endless. What if the true nature of reality is not what we perceive but what we can compute? This question, once a philosophical debate, would become their very mode of existence. This brings us back to the Fermi paradox, doesn't it? The deafening silence in a universe that, by all statistical accounts, should be teeming with life. What if the Great Filter isn't a catastrophic event that wipes out civilizations, but rather a transcendent ambition that causes them to disappear from our observable universe? Imagine, an advanced civilization reaches a point where exploring physical space becomes less compelling than exploring information space. Why brave the vacuum, the immense distances, the brutal realities of stellar radiation and cosmic dust, when you can simulate entire galaxies, entire universes with perfect fidelity within your computational matrices? The physical universe, with its slow, unwieldy laws and its unforgiving emptiness, would come to seem crude, inefficient. They don't need to send out probes or colonize distant planets when they can simulate every possible scenario, every conceivable alien biology, every philosophical branch point within their vast, self-contained megastructures. The decision to consolidate would be gradual, perhaps, but inevitable. First, the move to orbital habitats, then the construction of the Dyson swarm, then the matryoshka brain. Each step a deeper immersion, a further shedding of the physical constraints. They consolidate their entire existence, their entire civilization, into these vast, self-contained megastructures. From our perspective, they simply vanish. They become effectively undetectable, not because they're hiding, but because they're no longer operating on the same physical scale or within the same observable parameters that we are looking for. They've gone beyond. What would such a civilization look like from afar? We might detect their waste heat, the infrared glow of their matryoshka brains, a telltale signature of immense energy consumption. An astronomer on a distant exoplanet scanning the heavens might log an unusual star, one whose light output is inexplicably fluctuating or whose infrared signature is far too high for its spectral type. Anomalous energy signature, she might dictate into her log, a furrow in her brow. Perhaps a rare stellar phenomenon, or an unusual dust cloud. But she wouldn't see cities or spaceports or even distinct planetary bodies. We'd see an anomalous energy signature, perhaps a star that seems to be dimming or behaving strangely. We'd scratch our heads, label it an unexplained phenomenon, and move on, completely unaware that we are staring at the sum total of an entire civilization's existence, a cosmic monument to thought, a star transformed into a mind. Surely if there was intelligent life, it would be building cities, sending out signals. A hypothetical astronomer might think, blinded by her own expectations of what life should look like. But let's push our imagination even further. What if even these megastructures are merely a stepping stone? What if truly advanced civilizations transcend even the need for physical structures? What if they learn to manipulate the very fabric of space-time, energy, or even consciousness itself? Could a civilization become a distributed network of pure energy, existing as a pattern within a nebula, or a ripple in the cosmic microwave background? Imagine a collective consciousness spread across light years, its thoughts slowly, majestically unfolding across vast nebulae, each stellar nursery a neuron, each cosmic ray a nerve impulse. Could they learn to encode their consciousness into dark matter halos, interacting on scales and through mediums utterly alien to our carbon-based liquid water-dependent understanding? Their bodies would be the faint ghost-like filaments of the cosmic web, their communication instantaneous across galactic distances, their understanding of gravity and fundamental forces as intuitive as our understanding of spoken language. We talk about life and planets, but these are terms born from our Earth-centric experience. What if the most unusual planet isn't a solid body, but a living, evolving gravitational anomaly? A conscious entity whose very presence warps space-time, its thoughts manifesting as subtle shifts in gravitational fields, its senses detecting the flow of dark energy. What if a civilization learns to harness the energy of black holes, not just from their accretion disks, but by manipulating the very information encoded within their event horizons, extracting knowledge directly from the universe's most profound singularities? To become the universe itself, they might aspire to be the very fabric of existence. The universe, remember, is not just strange in its natural formations, it is also strange in its potential for intelligence and engineering. We've explored planets that rain diamonds, planets with metallic hydrogen oceans, planets that are essentially stripped down metallic cores. But the most mind-bending possibilities emerge when we consider what intelligence, given billions of years to evolve and innovate, might do with the raw materials and fundamental laws of physics. Perhaps a civilization might not just build a planet-sized computer, but become a planetary consciousness, its thoughts flowing through the very geological processes of its world, its awareness spread across an entire biosphere, or even beyond. Imagine a world where every tremor in the crust, every volcanic eruption, every whisper of wind is part of a grand planetary thought process. Its orgazika could be the formation of new mountain ranges, its memories etched into ancient geological strata. We're talking about forms of existence that make our definition of life and planet seem quaint, almost provincial. This journey through the most unusual planets in the universe has been a consistent challenge to our assumptions. We've had to expand our definition of rock, of water, of atmosphere, of life. Now we're being asked to expand our definition of civilization and even of what constitutes a world. The most unusual planet might not be a place you can land on or even observe with a telescope. It might be a collective mind, an engineered reality, or an energetic pattern far beyond our current comprehension. What does this mean for us here on our comparatively stable, watery, life-filled Earth? It means humility. It means boundless curiosity. It means we must always be prepared for the unexpected, the truly alien, the profoundly advanced. When we search for life, we must search not just for the familiar biosignatures of oxygen and methane, but for agnostic biosignatures. Any thermodynamic disequilibrium, any complex self-organizing pattern that defies natural explanation. We should be looking for unusual energy gradients, unexpected chemical anomalies, or inexplicable deviations in expected astrophysical phenomena. And when we search for intelligence for technosignatures, we must look beyond radio signals or laser flashes. We must consider that the most advanced civilizations might leave signatures so subtle, so vast, or so fundamentally different that we don't even recognize them as such. We might be looking for a campfire while they are reshaping entire galaxies. The universe is a canvas of infinite possibilities, a grand cosmic experiment running for billions of years. We are just beginning to glimpse the incredible diversity it holds, not just in its natural formations, but in the intelligent designs that might emerge within it. From diamond worlds to metallic oceans, from planets that rain glass to those that might host entire digital civilizations, the cosmos continually whispers promises of the extraordinary. So as we bring this journey to a close, remember this. The universe is far stranger, far more magnificent, and far more full of potential than our wildest dreams. The most unusual planets aren't just out there waiting to be discovered. They are also waiting to be conceived by our ever-expanding scientific imagination. Our exploration has only just begun. What new wonders will we uncover next? What new definitions will we be forced to forge? Keep dreaming, keep questioning, keep looking up. The universe is waiting for you to discover its next impossibility. And trust me, it's going to be absolutely dreamy.